In our final part of Section 20, we're going to branch outside of the Milky Way and discuss the galaxies and what we know about them. So, if you recall from our brief of a history lesson, we originally thought they were just other nebulae, other type of gas clouds that were inside the Milky Way. Now we know that there are more than 200 billion galaxies in the universe, representing trillions and trillions of possible stars throughout the cosmos. So, we're going to classify our galaxies into three main groups. We're going to call them our spirals, our ellipticals, and then our catch-all, just the irregulars. And we're going to have a lot of sway in how we classify these because, well, it's kind of difficult sometimes. We're going to have to figure out what the heck we're looking at. So here we're looking at a deep field image from the Hubble Space Telescope, and just based on the shapes that we see, we have to try and categorize them. But this is akin to a bunch of coins being thrown in the air. Sure, several of them are pretty easy to identify. They're facing us. But anyone want to wager what this coin is? Or this one? And how can you tell, in terms of galaxy, if we're looking at one galaxy with a weird shape, or two galaxies and one's just in front of the other? So this is the kind of problem that we're dealing with when you're trying to categorize the galaxies. But Hubble came up with a nice scheme that we still really use today. And he sorted them based on basically their brightness, how tight their bulges were, and the tightness of their arms as well. So on the far left-hand side of the scale, we're going to have our ellipticals, almost spherical in shape. And as you go towards the right, you're going to have the galaxies that get a bit more elliptical and elongated. And then we can branch up. We'll start becoming spirals. We'll have the nice identifying arms of the galaxies. And our spirals, we split them into two types, right? Are just regular types of spiral galaxies, or spirals that have these kind of bar shapes. There's this almost bar that's just stapled across the center of the bulge. So, some peculiar ones of interest talk about the SAs. These are sometimes called lenticular galaxies, partially because of how they can kind of act like a gravitational lens of light, bending the mass or bending space-time around them, and the very indistinct forms of their arms. They're there, but they're just a step away from being ellipticals. On the other side of the spiral galaxies, we have the SC categories. Around a very small central bulge and just tons of these loosely wounded arms. The arms, while present or there, are very long and very loose, whereas, say, our galaxy or Andromeda, they're very well-defined arms. In fact, the Andromeda galaxy is what we call an SB spiral galaxy, whereas the Milky Way is somewhere. It's either an SB or an SBB, a spiral bar galaxy, the B for bar. We're still figuring out the details, which branch of the spiral galaxies the Milky Way falls into. Let's look at the details of specifically a spiral galaxy. In this image, we have what we call a edge-on. Think back to the coin slipping through space. Same to these galaxies. We're looking at this one on its edge, but you can still clearly make out the central bulge and the arms of this galaxy. So, like the Milky Way, spiral galaxies, they're going to consist of that central bulge, that halo of material and older stars around that. You'll have the disk of material at the center of the galactic plane, and then the spiral arms, right? So you're going to have interstellar matter present throughout the disk, the star-forming regions. And in our spiral galaxies, the gas is generally colder, versus the elliptical galaxies, they'll have a bit of a higher temperature. And what you'll notice in spiral galaxies are these basically bright emission nebulas. Hot young stars concentrating on those arms. So regions of higher density means that you're going to have more active star-forming regions. So the spiral galaxies are generally going to be newer, younger galaxies, and they're going to be producing lots of new stars. Right. And matter in the arms, they'll have a very rotational pattern. Yes, this is kind of repetitive from the Milky Way, but we want to distinguish the difference between our spirals and our other galaxies. So we really want to emphasize that the arms have a nice cohesive pattern of rotation to them. And our spiral galaxies span anywhere from 10,000 light years to 300,000 light years in diameter. So, question for you now, right? Let's say I'm looking at a spiral galaxy, right? And I've still got Kepler's law, still a useful tool. So, I look at the motion of this galaxy, and I think back to what Kepler's law. What information can I glean from that? What does it give me? Go ahead and pause for a moment, come back. So we're going to use Kepler's third law specifically. And the third law just says, hey, it turns out that the rotational period, the square root of that, is proportional. There's the proportionality constant to the cube of the semi-major axis, effectively the diameter. So, I guess the radius, diameter is double that. So, think about this for a moment. When we look at the galaxy, we can immediately identify its diameter. We look at the distance between all these different stars from edge to edge, and so we can get the size of it without needing Kepler's edge. So, boom, not getting the semi-major axis. We're about that rotational period. Galaxies can take thousands, millions of years to rotate around, but we can use Doppler shifts to calculate the rotational speeds. So once again, don't need Kepler's laws to get that. We use Doppler shifts and look at the rotation rate of the galaxy. So that leaves us with the mass or recessional velocity. Velocity isn't even a part of the equation in Kepler's third law. So we're left with the conclusion that by just observing the galaxies, we actually figure out how massive they are. Very powerful trick. Moving on to our next category, the elliptical galaxies. They're going to be a bit more spherical in shape, or elliptical in these cases. And so there's no well-defined arms. And when you look at matter in the elliptical galaxies, they're not going to have any kind of rotational pattern to it. You'll see some stars in there that could rotate this way. They also could rotate that way or that way. There's no coherent pattern to the rotations of these elliptical galaxies. Right. But they still have that bright central bulge, a strong luminosity at that center of the star. And because of that, the gas is generally going to be a lot hotter because of the random, almost chaotic motion of these. They're also going to be generally older galaxies. They're going to have little to no stars forming in them. And one way that we suspect elliptical galaxies come out of is think back to those collisions of galaxies. Elliptical galaxies might be partially formed by being smashed together of older galaxies just getting to their old age. And these things, they span the full spectrum of sizes in terms of galaxy size. Anywhere from just 3,000 light years long to 700,000 light years in size. So they go from the smallest to the biggest. Right? And we'll often find these elliptical galaxies are found in clusters of galaxies. Finally, there's our last term, that irregular galaxies, that catch-all. And here is just the little galaxy. This is just a star in the foreground between us and the galaxy. Right? So here it is. It's not a nebula. It's not a collection of dust. It really is a galaxy with some cohesiveness to it. And basically, irregular is just a catch-all term for things that don't fit nicely into being these elliptical shapes or spiral shapes. They're not balls of gas because there's stars in them. They're gravitationally bounded. So one thing we have noticed is that the further out we look in the cosmos, the more we start to find these irregular galaxies. And these things are going to be usually lower masses, lower luminosities. There's a correlation there. But they will contain a reasonable amount of both population 1 and population 2 type 2 stars, some young and some older. So there's a huge question of what forms the irregular galaxies. What is the gravitational dynamics that allow something like this to be cohesive but not really have any well-defined shape to it? So now let's gaze our attention towards the center of the galaxies. Every type of galaxy is always going to have some kind of brighter, more luminous region towards the center. Our galaxy, in fact, towards what's called Sagittarius A star, Sagittarius being the constellation where we find this, you'll notice this bright spot emanating from the center of the Milky Way. People were trying to figure out, what is this? They looked at it in the infrared, the radio, and X-ray spectrum. They kept finding this huge glow here, and it was persistent, and it wasn't a type of star. It was too big to be a star. So people started looking at other tricks. They took data over the course of almost 2 decades of stars near the center of the Milky Way. And just like we use Kepler's laws to get the mass of the galaxies, we can do it for the mass of whatever it is all these different stars are orbiting. You might recall that I said in spiral galaxies they all have a rotational pattern, but do recall as well that I said that that applies for the thin disk of the spiral galaxy. Here we're looking at patterns near the central bulge, literally outside the central bulge of the galaxy. So you're looking at how stars are moving around near, at that center. Well, we can calculate these orbital radii, calculate the periods of the orbits, and we'd find that there is this insanely massive object. We know that there's something that's about 2.5 light minutes in diameter at the center of the galaxy. For perspective, that's smaller than the radius of Mercury's orbit. And yet this thing that's smaller than Mercury's orbit is going to have a mass of almost 5 million suns. And that's where we get this concept of this supermassive black hole present at the center of the Milky Way. Yes, I literally just said that it's glowing. And it really is. The centers of these galaxies are glowing. But to have that much mass concentrated in one location means it also has to be a black hole. So how these black holes form, where they come from, is a field of constant research right now. As for the glow, how can it be so powerful? Once again, don't walk away from this course with a misconception that galaxies are these gobbling monsters that are just shoveling everything into them. No, they're gravitational objects and things can orbit them. So this comes in the concept of what we call active galactic nuclei and a related term quasars, right? So an AGN refers to just that small center of the galaxy. You're going to have an increased luminosity, and it's not something being produced by the stars. The luminosity, the persistent source of radiation coming out, is believed to be matter accreting, falling towards a supermassive black hole. And as they fall in, they get superheated and become this constant source of light across literally the entire spectrum. We've seen AGNs that produce radio waves all the way up to gamma rays. We see the full spectrum because there's so much energy of material falling into this. So to summarize everything in section 20, we've been studying the Milky Way, and through trying to figure out the shape and the structure of the Milky Way, we inadvertently found how big the universe is. And we know beyond a doubt that the Milky Way is a spiral galaxy, without ever leaving it by just mapping the gas that's floating around inside the Milky Way. Speaking of that gas, it's mostly hydrogen, and so it emits that special 21 centimeter hydrogen line. That line due to the electron spin flips. And this line here is not susceptible to dust, so it allows us to easily map where all the material, all the gas in the Milky Way is moving. Another point is that we've associated that stars' locations in the Milky Way actually correlates with the age of the star and its chemical composition, the abundance of heavy elements that are present there. And finally, we've classified galaxies into three categories: our spirals, our ellipticals, and our irregulars. And that at the center of every galaxy, there must be these supermassive black holes. So, that's the end of section 20, and we'll see you all next time.